So today's class is mostly talking about angle relationships in circles. So the first kind of thing we're going to look at is the inscribed angle. And what is an inscribed angle? So here's my circle. Here's my angle. Notice that the vertex is on the circle. And the sides of this angle contain the chords of the circle. So this is an inscribed angle. It's inside that circle. As another word we need to know is the intercepted arc. The intercepted arc is found by an inscribed angle. So you make your angle. This red piece here is what I call the intercepted arc by that inscribed angle. Because of that angle, I now have this up. Okay, so just vocabulary. Inscribed angle, if the vertex is touching the circle. The inscribed arc is the arc formed by having that angle. Okay, so we'll be using those words. So here's our first theorem, and let's just talk about it first. The measure of an inscribed angle. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. Oh. So remember, the intercepted arc would be the arc formed by that angle, and this angle in here is half of it. So if we go to our little paper here and draw that picture, so we start with a circle. We're going to draw an inscribed angle. I'm not very good at the drawing, so I'm doing the best I can. I'll try and use the same things that the picture on your notes used. On your notes, it's showing that the circle, this does not have to hit the center. The center could be anywhere. It could be the center, it doesn't have to be. So the way this works is the measure of angle D is 1/2 the measure of arc AB. So if arc AB is 20, then angle D would be 10. Half that arc. If you know the angle, if this was, say, 50, angle D was 50, then the arc would be 100. So don't confuse this with the central angle theorem, which I think we've got up here someplace. Is this somewhere? We don't have the central angle theorem on here, do we? A central angle, right, if you're at the center, then they're the same. If you're inscribed, you're half. Okay, so hopefully we got that picture in there. And let's go back to what we got here, which is an example. So this example is the middle of page 1 here. I've got my circle P. I want to find the measure of angle T, and this is angle T, the T not very well. So angle T, so we say this is an inscribed angle. Let me find its intercepted arc. Its intercepted arc is 48. So what's the measure of angle T? Going, yeah, Thomas? 24 degrees, because it's half your intercepted arc. Everybody know where we are? Yeah? Give me a nod something. Yeah, I get it. Nothing. Okay. I'm going to assume you know where you are. Okay, find the measure of arc QT. So I want this arc. Now I'm looking for where's its intercepted angle. Oh, that's this one. So if the intercepted angle is 50, what's the arc intercepted, or the inscribed angle is 50, what's the intercepted arc? 100. So see how that works? Question? No question? Okay. Let's see. What's next? Okay. So this theorem is, I like this theorem only because it's very intuitive, I think. This theorem says that two inscribed angles of a circle intercept the same arc. Then the angles are congruent. All right, let's draw that picture. Let's see if we can draw that picture here. So you have your circle, and I've got an inscribed angle, and I've got another inscribed angle. And let's see, what should I call that? I will call it A, D, C, D. Now this theorem says that the measure of angle D is going to equal the measure of angle C, or you can write it as angle D is congruent to angle C. Either way, this one and this one. And this is one you can rediscover. So look what's going on here. So just look up for 1 second. I know you're drawing, which is good. But look at the angle D. That's an inscribed angle. Here's AB, its intercepted arc. Well, the intercepted arc here has another inscribed angle. So you can rediscover this one. Let's say you know that that one is 50 degrees. I'll make it up numbers. Then what would the arc be? 100. Well, based on this intercepted arc, I could go back to another inscribed angle that's also going to be 50. It's going to be half of it. So you can get there pretty easily if you can't memorize the theorem. Okay?
This is the transfer theorem of consequences, so which is
Yep. Yep, it is. So again, this one I think is a little bit easier. If you remember this one, you should be able to get back to this one. If you remember the theorem, then you're just a little bit faster. Okay, so that's that guy. And so we got an example of that. So the measure of W, X, Y, Z, this is the second one on the middle of the page there. Now, it's the same intercepted arc for both, so there's like nothing you have to do. It's 72. But think about it if you don't remember. So if you don't remember that little theorem, this is 72. So what's this arc measure, WZ?
44.
Right? Double it, 144 degrees. And then to find this intercepted arc, it's half of this at 72. So this one you can get back to, I think, somewhat easily. Okay. Not too bad. More theorems because it's fun. Here we go. And another theorem. A right triangle is inscribed in a circle, meaning that it's inside it. So when you inscribe a polygon, that's inside. Circumscribe would be if you put it outside. But if and only if, biconditional, the hypotenuse is the diameter. Oh. So if this is the hypotenuse, where's the right angle? Angle B. So let's get that thing drawn here. Oops, we're on the back. I'm going to draw this guy. I'm going to draw a diameter. And then you can draw any kind of inscribed angle based on that. This will be a right angle, if and only if. Which means if you have this situation and this is a right angle, then this must be the diameter. And let's just think for a moment why that's true. Why is that true? This one I think is somewhat easy to see why that was true. Because again, those we have to memorize the better. Maz, what do you think?
If the point is anywhere else, it wouldn't be a hypotenuse.
Well, let's see. This is a diameter. Well, how do you know that's 90? Christian, how do I know that?
Because if it's a diameter, then each side, arc is 180 degrees into the semicircle, so the inscribed angle would be half that.
Exactly, perfectly said. So because this is a diameter, it's a semicircle, and this is now an intercepted arc of this inscribed angle, so half of it would be 90. So that's, again, if you have trouble remembering them. This is a great one, though, because whenever, you know how you mark diagrams, I see a diameter, I see this right away, put in that right angle. Right away do that. Okay. And then this is, we'll do this one before lunch, our final one before lunch. A quadrilateral can be inscribed, get inside a circle like this, if and only if another biconditional, its opposite angles are supplementary. Okay, so again, working on the picture. So if you have any quadrilateral inscribed, meaning it's inside, and I'm trying to make it not look like anything, right? Anything. So I'll call it ABCD. So the measure of angle A plus the measure of angle C is going to be 180. Get opposites. And the measure of angle B plus the measure of angle D is also 180, supplementary. This plus this is 180, this plus this is 180. Can anybody kind of think about why that is? And again, if we can think about the why, it's less memorized. What do you think?
We meet at equal points, so it means the 180 so they would have to be congruent. Or not.
Well, they're not congruent. You're on the right, very much on the right track. Jerry, what do you think?
Draw the diameter between AC.
Okay, we're going to draw this. Okay.
Yeah. So then.
And this plus this, right? This piece plus this piece equals what? Well, the circle, the arcs. 360. And I know these are half, right? The angles, the intercepted angles have to be half of that 360. Because that's my rule. Right? Yeah, I mean, I'm just trying to simplify it up there. Because it equals up to 360 and I'm intercepting both sides, I'm taking half. I don't know half of what exactly, but they will add up to 180. Let's say half those arcs. Yeah?
So like half of arc ABC would be
Something.
B, and half of ABC would be D.
Right.
If both circles 360 for that point.
That's exactly right. Okay. And I'm going to let you go one moment, but hang in there, hang in there. I think we have the example. You know what? When you come back, actually just try these examples, okay? So, because that's a diameter, got an intercepted arc at 90, 40, by that corollary that says if you have a right triangle, the acute angles add up to 90. Okay, find P and Q. This is an inscribed quadrilateral. Inscribed quadrilaterals, opposite angles are 180. So if I start with this one, P plus 110, that's supplementary. So I can subtract the 110. Looks like P will be 70. I lost my place here. Okay. And then, oops. I still lost my place. Okay. And then going this way, D plus 95 would also be supplementary. So that's 180. Subtract that. D is 85. Is that right? So that was part B on the bottom, right? We're on the bottom here on page 1. This guy here, same thing. Inscribed quadrilateral, opposite sides will be supplementary. So we'll start 4y plus y would be 180 degrees. So 5y is 180 degrees. So then what's y? 36. 180 divided by 5. And then going across this way, these are also supplementary. So 6x plus 3x will be 180, or 9x is 180, so x is 20. And let's see what we got here. Same thing. I don't want to be so many. Okay, this one, 10x plus 8x, those are my opposite angles. They will be supplementary, so 18x is 180, so x is. And then now I'm going this way. This plus this is 180. So 2c minus 6 plus c is 180. So 3c equals 186. Yeah, just add that 6 in one step there. So c will be 62. Is that right? Yeah. I got it right? Okay. So again, it's just, they're not difficult theorems, but we just have to remember what they are. The more you can understand where they come from, the easier it will be to remember them, in case you need to rediscover them. So, new theorem. Oh, yeah, this one is slightly trickier than the other. Might be a little bit harder to see. If a tangent and a chord, so here's a tangent, here's a chord, if they intersect at that point of tangency on the circle there, then the measure of each angle formed is half the measure of its intercepted arc. So, before we put this on the paper, let's just think about it first. So, looking up. We can think about this. Here's my tangent, here's my chord. Look at this first before you copy it on the paper, just so that we can put something more. So that you kind of see what's going on here. It's a little harder to see. So chord, tangent, here is an intercepted arc, right? So this angle 1 is half the measure of arc AB. And you have 2 arcs, right? And 2 angles. So this angle on the other side, same thing. Angle 2 is half the measure of arc BCA. Now I can draw it, now that I kind of understand it. So you've got your circle, you've got a tangent, there it is, and you've got a chord, and they meet at that point of tangency here. So if I call this A, and this B, and we're putting another point here just so I can name the major arc. So if that's angle 1 over here, and this one's angle 2, the measure of angle 1 is half the measure of arc AB. So if that's 100, then this angle would be 50. Same thing the other way around. The measure of angle 2 is half the measure of arc AC. So if this was 200, then that angle would be 100. Yes, sir?
For the first example, we don't know what arc they are.
Okay, hang on. I haven't gone to examples yet. So anyway, that's what the theorem is. So, finish drawing this in here so you've got it on your one little theorem paper. And then we will get to those examples because she's got a good point there. Give me a second to catch up. Okay, so this first example here. So I want to find the measure of angle 1. This 220 represents the entire piece here. So if this whole thing is 220, what's the measure of angle 1? 110. It's going to be half of that intercepted arc. Now that's kind of easy. They could have said, here's my picture, this whole thing is 220. I'm going to call this angle in here angle 2. What's the measure of angle 2? So how do I get that? There's actually a couple ways to think about it. What's one way to get there, Maz?
You take 360 minus 220.
Right, this whole thing is 360. So if this piece is 220, to find that it's 360 minus 220, which is what? 140. So then what's this measure here? 70. The other way to do it would be 220 makes this one 110, and this is a linear pair, so that one's 70. So there's more than one way to get there. Okay, let's look at this guy here. The second example, which is towards the top of page 2. Find the measure of EFG. This angle is 135, so what's the measure of this arc? Twice 135, right? So 270. And again, that's kind of the easy one. Here's the angle, find the arc. They might have said, find this angle. So if I want, well, find the arc rather. So I can either find this one and say, well, that whole thing's 270. This one from here to here. Entire circle's 360. 360 minus 270 is 90. One way to do it. Another way to do it would be to say, this is 135. This is a linear pair. So if this is 135, whole thing's 180, what's this angle in here? E.g., there's no letter here. What's this angle?
Subtract 135 from
45, right? And so this arc will be twice that angle. So you got two ways to get there if they kind of want you to get there indirectly. I mean, does that make sense? Because, you know, they're not necessarily all that straightforward. Sometimes you have to go around and find things. So, okay. A couple of you tries, give these a go. Just I put these in here because these ones are slightly harder. I'm just going to put the answers up so you can start comparing what you're getting with what I got, which make sure I'm right. So are there questions on this? This angle is half the measure of that arc. This angle, half the measure of that arc. This angle, twice that will give you the arc. So that's where those numbers are coming from. Okay, last bit. Intersecting lines and circles. So when you have intersecting lines in a circle, there's 3 different ways to think about what might happen. You might have an intersection on the circle. You might have an intersection inside the circle. And you might have an intersection outside the circle. And so what we're going to do based on these 3 situations is we're going to find the angle measures. Basically want to find what's this angle, what's this angle, and what's this little angle over here. Question?
For the first theorem, shouldn't it be intersecting
Hang on, let me get there first, hang on. So he's a little bit ahead. But those are the angles we're trying to find here. So let's look at this theorem. So if you have a situation where the lines intersect, and now you have the point of intersection inside the circle. This theorem says, and again, before you copy it on your paper, just look up for a minute to make sure we understand it. Okay, everybody's looking up here? Yeah, we're not drawing again on this little thing? Okay, so intersecting, point of intersection, notice it's not necessarily the center. I guess it could be, but it doesn't have to be. So you take this arc, AB, and that arc, DC. You take those 2 measures and add them, and then you divide by 2. You'll get angle 1. You'll also get its vertical angle, so you get the measure of those angles. If you wanted the measure of angle 2, you'd add the measure of the arc AD plus arc BC. Add those 2 things together, divide by 2, you'll get the measure of angle 2. So now we can maybe draw a picture. And then you had a question about that, Jared?
Should be arc, It says that you should part of the intersection size to go on
No, I'm looking for the, the intercepted arcs. Yes, you're right. I should say arcs. Okay, so let's see here. What do we call A, B, C, D? I'm just going to put a 1 here. So the measure of angle 1 equals the measure of arc AB plus the measure of arc CD divided by 2. You're basically averaging those arcs. It gives you that angle. It will also give you its vertical angle. You could write it the other way if you want to as well. But that's it. Add the arcs, divide by 2. And you'll get those angles in here. So, come back here, intersected arcs. just looking at some of the examples, while you're still working there, that's okay. This one says, and I'm in the middle here of page 2. No, I'm not. I lied, I'm on page 3. Ooh. I'm on page 3, top of page 3. I want to find these missing angles 2 and 1. Well, I know how to find angle 2 because I know these two arc measures. So you're going to add 115 plus 97, and you're going to divide by 2, and that'll give you the measure of angle 2. So if you add those things together, you get, was that 210 over 2? That's 212 over 2, I think, yep. Which is, divide by 2, 106. So this angle here is 106 degrees. Well, so is that one, because they're verticals. So you found these two angles, 106. I also want angle 1. So I'm going to take advantage of the fact that these are a linear pair, angles 1 and 2. Whole thing is 180. This one's 106. So what's this piece? 74 degrees. So measure of angle 1 is 74 degrees, and the measure of angle 2 is 106. Okay, this is how you apply that. Another example here, it says find a missing arc. So notice what's going on in this little example here. I've got my intersecting lines here. I know this arc is 66 degrees. I don't know this. I'm just calling it arc 1. But I do know the angle in the middle here is 70, as is this one. So how do I find that? Well, I know that if I add the measure of arc 1 plus 66, and if I divide by 2, I'm going to get 70. So this plus this over 2 is 70. Multiply both sides by 2, get rid of the denominator. Subtract that 66, so what's the measure of arc 1? Whatever 140 minus 66 is, I think that is, I want to say 74? Is that right? Yeah. Did I get it? Okay. So that's 74 degrees. But I have to find this missing arc as well. Now I have one arc, but I don't know this one. I don't have the angle. Or do I? Right? How am I going to find this angle right here? Linear pair postulate. So that this whole thing's 180 and this is 70 makes this one 110. Makes that one 110 also. So that means that if I add 126 plus that arc 2, so the measure of arc 2 plus 126 over 2 will give me that 110. So the measure of arc 2 plus 126 is 220. And then I'm going to subtract that thing right there. Measure of arc 2 is 220 minus 126. I hope that's 94 degrees. Is that right? I think so. You'll tell me if I'm wrong, right? Would you like to tell me when I'm wrong? That's fine. Okay, so that's when you're intersecting inside the circle, that's how it works. Well, what if, and I'm kind of, we're jumping back to page 2 a little bit here just to see the other theorem. What if I'm outside the circle? And this one theorem looks at these 3 cases, really. So you can be outside, one's a secant, one's a tangent. You could be outside, they're both tangents. You could be outside, they're both secants. And one theorem covers it all. So if you have that situation, the measure of the angle formed is 1/2 the difference of the intersected arcs. So if you have a tangent and a secant, these are the intersected arcs. So this one, now look up here. If you're writing this on your theorem, you're not looking at what's going on. So please stop writing and look up. Okay, if you have this situation, write this down, just hang on. It's going to be a tangent and a secant, this red piece minus this blue piece, divide by 2, you get angle 1. If you have 2 tangents, it's this red piece minus this blue piece, divide by 2, you'll get angle 2. And if it's 2 secants, red minus blue over 2 is angle 3. Question? What? No, it doesn't. Okay, now we can write this down. Okay, if you haven't written it down, you can draw all 3, or you could just draw one general case. To me, the tricky piece about this is knowing it's subtraction rather than adding. See how this one's adding? This one now will be subtraction. So I'm just going to put some little markers here. And this I'm going to call angle 1. Right here. So it's going to be the measure of angle 1 will be the measure of arc BC minus that small one, minus arc AD, divided by 2. So if you're inside, you're adding and dividing by 2. If you're outside, you're subtracting and dividing by 2. Those are the zeros. So, if you aren't doing all of them, you could, I guess. But it's really kind of the same picture. Looking at some examples. Okay, we're back on page 3. Back on page 3. This is example C on page 3. Find the missing angle. I'm outside the circle where they intersect, so it's this arc minus this arc divided by 2. So 92 minus 43 over 2. Oh God, and I did this. 24.5? 5 degrees? And that'll be the measure of angle 1. 24.5 degrees. I got 2 tangents here. This one's a little bit trickier because it's kind of going to, I think, what Oz's question was. Isn't that going to be 180? If this whole thing, well, this piece is x, right? And it needs to be this big arc minus this smaller arc divided by 2. I'm going to get 45. But I don't know this arc. Or do I? Whole thing's 360. This piece is x. How can I express this outer arc? 360 minus x. So whatever this is, 360 minus that amount will give me this piece. So now it's this minus that. So be careful. So it's this piece here, 360 minus x, minus that x, divide by 2, and you should get this angle of 45. Multiply both sides by 2, combine like terms. I'm getting 360 minus 2x equals 90. If I add 2x and subtract 90, let's see, that's 270 equals 2x. Divide both sides by 2, looks like x is 135. So this one's 135. We need to find this one, 360 minus 135, we find another arc. With me with this one's a little bit tricky. Okay, this one I've got a secant and a tangent, and they're giving me both of these measurements. So this piece minus that piece, divide by 2, you're going to get 1. Let's see, that's a little hard to read. That's going to be 138 minus 66. Then divide by 2, you're going to get that measure of angle 1. What is that? I got 72 over 2? 72? Which is, I want to say, that is 36 degrees. And that's this. Okay, so you see the difference between those. If it's inside, inside, add them, divide by 2. If it's outside, subtract them, divide by 2. So it really is just 2 different theorems. And we're on to the U tries, so give them a go. See how we do. So these are, you can check your work while you're doing them, but please ask questions if you have them.